Welcome to this course on gas turbines and jet engines. Today is lecture number 53, which is the third lecture of week 11. Today we are going to compare the three major types of jet engines that we have studied. So, which is the turbojet engine, the turbofan engine and the turboprop engine. Okay. So, among this again we are going to compare the within turbofan also mixed type turbofan exhaust and unmixed exhaust type turbofan. So, 4 total engines we are going to compare numerically and then we will see how their characteristics compare. Okay. So, concepts which will be covered, the comparison of different types of jet engines. So, before we start the comparison, if you remember we had already discussed about the solution of design point calculations for the unmixed type of turbofan engine and later we have done for the mixed type turbofan engine, and for the mixed type turbofan engine the problem that we had selected we again solved it for the with the same parameters for the unmixed type turbofan engine also. Okay. The idea was to compare the two different types of turbofan engine with the same operating parameters, okay, same design and operating parameters. So, then we had also considered turboprop engine with all the same parameters except that the Mach number was taken to be lower, so that it is realistic. Now, we will quickly solve the problem for turbojet, the same problem for turbojet with the same parameters with any changes which are necessary, but otherwise keeping all the parameters same, and then we will see how all these values of the performance parameters such as the thrust specific fuel consumption and the specific thrust, how they compare between these engines. Okay. So, these were the problem parameters, okay, as shown here. This was from the mixed exhaust turbofan engine. So, I have listed the same parameter and then we will select whatever parameters are needed. So, instead of mixed exhaust turbofan, now we will have a turbojet engine, okay, and Mach number is 0.9, inlet conditions are fixed 222 and 226.2 kPa, 222 Kelvin. Now, we will fix the overall compression ratio as 16 because we do not have a fan here. So, we will fix the overall compression ratio as 16, T max we will have as 1400 K, pressure loss is 3% in the combustion chamber, calorific value is 43,000 kilojoule per kg, diffuser efficiency is 98%, compressor efficiency is 88%, there is no fan. So, this is not needed, combustion efficiency is 96%, turbine efficiency is 94%. Okay. So, this will be a single spool. So, this because it is a turbojet, only we are considering that one turbine is running the single compressor. Okay. Nozzle efficiency is 95%, any condition is not required because there is no mixing. So, we have to find the specific thrust and the thrust specific fuel consumption. So, all same parameters except the parameters which are not undefined or cannot be defined for a turbojet engine. Okay. So, let us start the analysis. Let us start by drawing the cycle quickly. So, this is the, let us say this is the ambient pressure P A and this is the diffuser process going from A to 0 1. Then this will be pressure P 0 A, this is the point 0 A and the actual pressure is P 0 1, which is shown here like this, and this is the point 0 1 S, okay, the artificially defined point to quantify the efficiency of the diffuser. Okay. Then apart from this we have the compressor. So, the compressor goes from 1 to 2, okay. Isentropic point, say corresponding point is 0 to S. Then the combustion process, there is a little bit of pressure loss. So, the conversion goes from 02 to 03. So, this is P 02 and this is P 03, slightly lower than P 02. Then we have expansion in the turbine from 03 to 04, this will be 0.04 s, and then expansion in the nozzle from 04 to 5, okay, this will be 0.5 s. We can also draw the corresponding 0.5 point here and the P 05. So, this is P 5, this is P 04. Okay. So, P 5 may be equal to atmospheric pressure or may be higher than that, depending on whether the nozzle is not choked or choked. If it is choked, it will be higher than that. Probably in this case it will be choked, because we have seen that for the other cases also it was choked, and in this case chances are more. Let us see. So, we start with the diffuser. Okay. We start with the diffuser. Diffuser calculations remain same. So, we can quickly do the diffuser calculation. So, we will find that T 01 is equal to 257. So, I am just writing down the values, you can solve on your own and then compare. 257.96 Kelvin. Okay. And P 01, so T 01 s we can find, T 01 directly we can find from T 0a, and T 0a by T a we know is 1 plus gamma minus 1 by 2 m s square. So, we have from there we find T 01, then we will find T 01 s and then P 01. P 01 is equal to 43.88. This is same as the turbofan cases, okay. Same for, because the diffuser function does not change here and the ambient conditions are remaining same, and we have also considered the same slide velocity. Now, P 02 is equal to 16 into P 01, okay, pressure ratio is 16. So, this is equal to 702.08 kPa. Okay. So, we will need this slide, this diagram again. So, what I am going to do is I am going to save this diagram onto the next slide also, and we will use this. In the next slide also. So, we will come back to the present slide, and P 02 we have found. The next thing that we have to find is T 02 s. Okay. So, from P 02 we have to first find T 02 s and then we will be able to find T 02. Okay. So, these are for the compressor. T 02 s by T 01 is equal to P 02 by P 01 to the power gamma A minus 1 by gamma A. Okay. So, P 02 by P 01 we already know is equal to 16. So, T 02 s by T 01 comes out equal to 2.208, which gives us the value of T 02 s. This comes out to be equal to, 569.62 Kelvin. Okay. So, T 02 s is found. Next we have to find T 02. So, for that we will take the help of or use the compressor isentropic efficiency. So, now we know that eta C is equal to 0.88, okay, same value as we had taken previously for all cases. So, from there you can find the value of T 02 to be equal to 612.12 Kelvin. So, this completes the calculation for the compressor. You can of course compare the values with the previous problems to see what type of values you are getting here. Then from the compressor we go to the combustion chamber, combustor. So, here what are the values that we will try to find? First is P03. So, P03 is, so there is 3% pressure loss in the combustion chamber. So, this is 0.97 into P02. So, this comes out to be equal to 681 681.02 kPa. Okay. What about T03? T03 is known to us. This is the maximum temperature of the turbine inlet temperature, is given to us as 1400 Kelvin. Okay. So, this is done. Then what is the next task? We have to find, we have to solve for the turbine. Okay. So, for solve for the turbine. So, for the turbine, before that, do we need to find anything else? We need to find the air fuel ratio or fuel air ratio. Okay. So, fuel air ratio, how do we find? F is equal to, so from energy balance, F equal to Cp of gas into T03 minus Cp of air into T02 divided by combustion efficiency into calorific value minus Cp of gas into T03. This comes from the energy balance, we have done it many times. Everything is known. So, Cpg is 1.148, T03 is 1400, Cpa is 1.005. T02 we have calculated right now 612.12. Combustion efficiency is given as 96%, calorific value is given as 43,000 kilojoule per kg, and these two also we have already stated. So, this comes out to be equal to 0.0250, okay, or 0.025. So, this is needed for the next step where we do the energy balance or work balance between the turbine and the compressor. So, for the turbine, from energy balance, what do we know? The work which is supplied by the turbine. So, mechanical efficiency multiplied by the work generated by the turbine, which is equal to mass flow rate 1 plus F into Cp of gas into T03 minus T04, right. So, this is the work which is supplied to the compressor. So, this is the work which the compressor is using for running, where the mass flow rate is 1 multiplied by the work done by the compressor Cpa T02 minus T01. So, here now what is known to us? T02 is known, T01 is known. Okay. What is the value of T01? T01 is 257.96, T02 we have found 612.12. Cpa is known, Cpg is known, T03 is known, 1 plus F is known, and E time is given as 1. Okay. This is given as 1. So, finally, everything is known except T04. So, from here we will find the value of turbine exit temperature, which comes out to be equal to 1097.52 Kelvin. Again, you can compare this with other problems if you want, okay, to get an idea about how these things vary. So, next we have to find the pressure P04. For that, we first need to find the temperature T04s. Okay. So, now isentropic efficiency of the turbine is 94%. From there, we will get the value of T04s, and this comes out to be equal to 1078.21 Kelvin. Okay. And from this we get the pressure from T04s and T03 we use isentropic relation to get the ratio of P 03 and P 04. So, we get the value of P 04 to be equal to 239.40 kPa. Okay. So, now we move on to the calculation of the nozzle. Okay. So, for the nozzle, we will take another color. For the nozzle, inlet condition is known T 04 1097.52 and P 04 239.4. So, we will start by assuming that the nozzle is choked. Okay, assuming choked nozzle. Assuming that the nozzle is choked, we see that T 04 by T 5 equal to T 05 by T 5, T 04 by T 5 equal to T 05 by T 5, because T 04 and T 05 was equal, because the stagnation temperature remains constant in the nozzle. This is equal to gamma g plus 1 by 2. Okay. So, which means that, and T 04 and T 05 we already know is 1097.52, okay, 1097.52. So, from here we get the value of T 5. T 5 is equal to 940 T 5 is equal to 940.87 Kelvin. Okay. So, this is found, but the pressure we have to see whether the nozzle is choked or not. So, if based on that condition the nozzle is choked, we are doing the calculation. So, T 5 is as the nozzle efficiency is 95%, we can say that T 5s is we can calculate it, and it comes out to be equal to 932.62 Kelvin. So, this is the temperature. So, from this we get the pressure, okay, P 5 using isentropic relation, and this comes out to be equal to 124.76 kPa. So, this pressure is clearly greater than the, so this is clearly greater than the atmospheric pressure, much higher than the atmospheric pressure. So, nozzle is choked, our assumption is correct, nozzle is choked. Okay. So, this is our final pressure, exit pressure 124.76 kPa. So, now we find the velocity V 5, assuming choked nozzle, V 5 is equal to C 5 is equal to root over gamma of gas R T 5, R is 287. Okay. You have to be careful with the values and units. So, this is equal to 599.96 meter per second. Now, we also have to find the density and the area, cross sectional area of the nozzle, because we have to find the pressure thrust. Okay. So, now density is equal to how much? Rho 5 is equal to P 5 by R T 5. Okay. P 5 by R T 5, P 5 is 124.76 into 10 to the power 3, R is 287 and T 5 we have calculated as 940.87. Okay. So, by Substituting these values, we get the value of density to be equal to 0.462 kg per meter cube. Now, we can write the area A5, which is equal to m dot h into 1 plus f, the mass flow rate, divided by rho 5 V 5. Okay. This comes out to be equal to 3.698 into 10 to the power minus 3 into m dot h, okay, in meter square. So, finally, we can write the thrust. So, total thrust F by m dot h, total thrust per unit mass flow rate of air through the hot section. This is 1 plus F V 5 minus V A, this is the momentum thrust, plus the pressure thrust. Here there is a very large pressure difference, so we expect a very large pressure thrust, P 5 minus P A 5 by m dot h. Okay. So, finally, we get the value to be equal to 346.16 plus 364, okay, large pressure thrust 0.45 Newton per kg per second of mass flow rate of air through the core section. Okay. So, we can also find the thrust specific fuel consumption TSFC. This is equal to F into m dot h by capital F. So, which is equal to, so F we have already calculated 0.0250 divided by F by m dot h is. So, this we can take the total, which is 710.61 Newton per kg per second. So, 710.61. So, this is equal to, or so the unit for this is kg per second per Newton, okay, mass flow rate per unit thrust. So, this comes out to be equal to 3.518 into 10 to the power minus 5 kg per second per Newton, and we know that we multiply it by 3600 to get it in terms of per hour, which is a more practical value. So, 3.518 to 10 to the minus 5 multiplied by 3600 kg per hour per Newton. Okay. So, this is equal to 0.1267 kg per hour per Newton. So, this is the value, and you can compare these values with the turbofan engines, two types of turbofan and the turboprop, and see what type of results you get. So, I have done the comparison in the next slide, comparison of the important parameters. Okay. Remember that we have kept all parameters constant and only new parameters have been defined when it is needed for that particular engine, otherwise all common parameters are constant except the Mach number, which for the turboprop only we have taken to be 0.6, for all other cases it is 0.9. Turboprop we have not taken 0.9, why? Because that will be not practical, turboprops cannot operate at that high Mach number. Okay. So, let us take a look at the comparison. So, with the same values, for turbojet we have obtained the exhaust velocity 599.96 meter per second. For the unmixed exhaust turbofan, for the hot section we have the velocity 533.7, which has to be lower than, or which is going to be lower than that of turbojet. For the bypass section the velocity is much lower, it is 327.7 meter per second. Okay. So, these are the two velocities for the unmixed exhaust. We can see that turbojet exhaust gas is much faster. Here the mass flow rate of air is less, but the exhaust velocity is high. Then for the mixed exhaust turbofan, the mixed air flow velocity at the exit is 383.01 meter per second. This is in between the two limits of the unmixed exhaust turbofan. And for the turboprop, so we can only find the velocity for the core section, jet section, where the exhaust velocity is very small, 212.9 meter per second. Okay. Remember, the aircraft is also designed to fly at lower velocity, 0.6 Mach number, and we do not know what is the velocity after the propeller, because it is not possible to directly find that, okay, but it is not going to be very high, because a very large amount of mass flow rate is happening and the thrust also is large, but this is due to the mass flow rate. Okay. Next is exhaust pressure. So, what is the conclusion from this? That from turboprop towards turbojet, the exhaust gas velocity keeps on increasing. Okay. What about the exhaust pressure? So, here by exhaust pressure I mean that if the nozzle is choked, that is, it is not at ambient condition, then what is the that pressure of the choked nozzle. Okay. So, for turboprop the nozzle is not choked, so the ambient pressure PA is the exhaust pressure. Then for mixed exhaust turbofan, this comes out to be equal to 44.92 kPa. Remember, what was the value for the ambient condition? In this case was 26.2 kPa. Okay. So, significantly higher than that. For the unmixed type, for the core section we have 45.7, which is slightly higher than this 44.92, and for the bypass section it is slightly lower than this 44.92, this is 44.68 kPa. Both are near to each other, but on two sides of this mixed exhaust valve. For turbojet on the other hand, we have a very large value, okay, very high pressure, because we are unable to utilize the entire energy that was present by having a conversion nozzle. We are unable to increase the exhaust gas velocity too much, and not much work was taken, because there are no fans or the mass flow rate through the compressor is less as compared to mass flow rate through the fan. So, the work required there was not very high. So, anyway, so this is much higher. Okay. So, again the same trend, gradually it increases towards the turbojet. Now, the momentum thrust per unit mass flow rate through the core section, okay, per unit mass flow rate through the core section, not per unit mass flow rate through the overall engine. So, here for the first case it comes out to be 346.16 Newton per kg per second. Then it increases for the unmixed type. Okay. Unmixed type is 278 from the hot nozzle and 247 from the cold nozzle. Mixed type is even higher, it is 603.31, and turboprop, from the propeller we get very high thrust 1956 Newton per kg per second, but the nozzle creates very small amount of jet thrust, only 39.8 Newton per second per kg per second. So, you can again compare the values. The specific momentum thrust keeps on increasing, the main component or the overall value, but the jet thrust here is very small for the turboprop. Okay. It is very small. On the other hand, remember that these are per unit mass flow rate of air through the core section. If we write this per unit mass flow rate of air overall, then we will get different values. Similarly, the pressure thrust, in the first case this is 364.45 Newton per kg per second, which is a high value, but relative to that mass flow rate it is a high value. For the unmixed type, the choked nozzle of the hot section gives a value of 175.26, lower than this 364, but the bypass duct is at a has a higher thrust generator, because the size of the bypass nozzle is very large. Okay, I have not written down here, but you should compare the size. Size will be very large as compared to the turbojet or the core section of the turbofan. So, this as a result, although the pressure difference is less, the thrust comes out to be much larger, 406.53, and the thrust is even larger for the mixed type, where we find that this is equal to 602.22 Newton per kg per second. Here the cross section area is very large, again even larger. So, we get larger thrust, although the pressure difference is less as compared to that of turbojet. For turboprop, there is no concept of pressure thrust in the jet, because the nozzle is not choked. Then finally, the two important parameters, one is the thrust per unit mass flow rate, total thrust per unit mass flow rate. You see that this keeps on increasing as we go from turbojet to turboprop. Turbojet is lowest 710, then 1107, 1205 and 1996 for the turboprop. So, again remember that this is per unit mass flow rate through the hot section. If we take overall air, then the trend will be opposite, because more air flows through the turbofan and even more air flows through the turboprop. In that case, turbojet will have the highest specific thrust and gradually it will decrease. However, there is no ambiguity about the thrust specific fuel consumption, because per unit thrust this is the amount of fuel that will be needed, and fuel consumption is clearly more for the turbojet. It is lower it has lower efficiency as compared to the unmixed type, which is next, then the mixed type is slightly better, and then the turboprop, which is very good, which has very good fuel efficiency or very low thrust specific fuel consumption, more than 2 times lower as compared to that of the turbojet. So, this is the comparison of the numerical values. So, in real life, when is these engines used? So, turbojet generally the propulsive efficiency increases at a high Mach number. So, beyond 1 we get very good propulsive efficiency if we keep on extending. Turbofan, high bypass turbofan used for commercial application. So, low bypass turbofan will be similar to turbojet, slightly on the upper side. High bypass turbofan will have higher efficiency at moderate Mach number, but after some time, means at very high Mach number it cannot be used. So, if it is less than Mach 1, then the high bypass turbofan is more efficient. Turboprops are more efficient at lower Mach number like 0.4 and 0.5, but turbofans become more efficient at higher Mach number or moderate Mach numbers below Mach 1. So, based on this we can see that we had calculated for a low value of Mach number. For our turboprop we had actually taken Mach number 0.6, it is somewhere around here, but that is why we got the efficiencies and fuel consumption to be less. This is propulsive efficiency, but this also plays a very important role in that. So, prop fan is another type of engine which is a modified turboprop, which is designed to fly at near sonic speed. This we will briefly discuss in one of the next classes. So, this is an idea about how the propulsive efficiency vary, and based on this we can select what type of engine we need for which Mach number application. Finally, to summarize, the jet engine means comparison between these 4 cases. So, turbojet we are comparing now low bypass turbofan, because this is the main distinction, and high bypass turbofan, they are very different in characteristics, and turboprop. So, primary thrust is exhaust jet. For the turbojet there is no other thrust, of course pressure thrust is there, but that also comes from the exhaust. Then in low bypass turbofan we have fan thrust plus the exhaust jet. High bypass is mostly fan, very less amount of exhaust jet, and turboprop is almost everything is from the propeller, very less amount from the core section. Bypass ratios, by definition it is 0 for turbojet, 0.3 to 1 for low bypass turbofan like those used for military aircraft, 5 to 12 for passenger aircraft high bypass turbofan, and very high effective bypass ratio of the order of 100 for turboprops. Propulsive efficiency is low, and then it for the turbojet keeps on increasing towards the turboprop, that is what we have seen. Fuel efficiency also keeps on increasing at low speeds. Optimal speed for turbojet is high subsonic to actually better, it is at low supersonic or moderate supersonic speed. Low bypass turbofan is good for high subsonic and low supersonic speed. High bypass turbofan is for high subsonic speed just below Mach 1, and for low subsonic speed we have turboprop. Noise level also depends on the exhaust velocity. So, it is highest for turbojet and gradually goes down towards turboprop. And we have already discussed typical applications. So, early jet aircrafts used to use turbojet, nowadays we mostly use low bypass turbofan fans for military aircrafts like fighter aircrafts, and for commercial aircrafts or transport aircrafts we use high bypass turbofan, and for short distance aircrafts and utility aircrafts we use turboprops. Okay. We will still study a few more types of jet engines like ramjet, scramjet, pulsejet, etc. But these are the main types that we have discussed today. That is why we have done a comparison with this, because these are the types. Almost always you will find that these are the types that are used for aviation industry. Okay. So, with this we come to the end of today's class. We have compared the different widely used jet engines today, and we have seen how they quantitatively compare for the same flight conditions, and how the specific thrust and the thrust specific fuel consumption changes. These are the references. Thank you.